Hello, everybody. Welcome to the virtual SI session for 146. As you can notice, it's only me today. Shivanku wasn't able to make it, so let's power through it. I'll get right into it. I won't take much time, and you guys have need the time to study, so we'll do that. Let me just ask, everybody can see the slides through my screen, right? Okay, cool. All right, I'm just going to talk a little bit about what I'm going to do throughout this virtual session, and we'll start going through the topics. Okay, so what I'm going to do in this session is not really go into too much details of what every specific topic or maybe every specific algorithm. That's something that cannot be covered in one session. But what I want to do is maybe look at the entire semester and put everything together and how everything connects to each other, and also focus on like the important ideas that I know that came up with the midterms and finals, and from my experience. And yeah, that's it. Then also what I have in the slides is like a couple references to important sections of the book that everybody should check out. So that's really what this session is about. So nothing very technical, it's just high level, and it will like piece everything together throughout the semester. Okay, let's start. So, so that's the goal of the session. Then after that, I'm gonna talk a little bit about finding the runtime and what we used to do it. Talk a little bit about the sorting algorithms that we have and what should we know about it, and touching on the data structures that we took and what should we know about it too, and graphs, the algorithms that we have in the graphs, and what specific cases these algorithms should be used. Then after that, I'm going to touch about the general idea of dynamic programming and some ideas related to MP completeness. And you might notice that maybe some ideas are not, I don't have them covered thoroughly. It's probably because it's not very important. It's not worth spending a lot of time talking about that specific idea. That's probably the case for dynamic programming. Okay, let's start. Finding runtime. All right, so that's the first thing that we took in this class. We spent a couple of weeks about talking about the runtime of algorithms and how should we find it and the different ways we can find it. So in a way, I put everything down in one slide, and let's see. So whenever we want to try to find the runtime for an algorithm, we need the recurrence relation, which is going to look something like this. Most likely, the recurrence relations will have a term or more inside of it that is the same term as the outside, which indicates that this is a recursive call. And that's really what makes us look for the runtime. Is if there's no recursive call, we have the equation will tell us the runtime, and that's it. But because of that recursive call, which is the function of t that's called in the body of t of n, it makes it a little more complicated, and we want to know when does this end and how we can calculate the runtime. So to start finding the runtime for a specific algorithm, we need the recurrence relation, or we can just have a random recurrence relation that we can start working with. So that's definitely a question that's going to show up, 1 or 2. So it's important to not maybe lose a couple points on this one, because they should be easy, maybe except the algebra part of it. So the first instance that we face a recurrence relation, our thought should be, can we apply Master's theorem on it? And if we're gonna apply Master's theorem on it, it should be of this form. A and B and the function of n to the end. If it's in this form, go to master's theorem right away, apply it, and find which cases that the recurrence you're working with is from. And to find a couple more examples, actually like 5 or 6 examples, I believe, is if you checked out the book, pages 95 and 96, they have a couple cases of master's theorem broken down, and you can see how they're working through the problem and applying the logic. And now, if the recurrence relation does not fit this form, what we're gonna do is look for the substitution method, which is a little easier than recursion tree, if you guys remember. So with the substitution method, it works if first master's theorem doesn't work, so we go for the substitution. And we want to go for the substitution also if the question says prove this relation is big O of something. So if it's telling us to prove that it's big O of something, I'm going to take that big O and start substituting it wherever there is a recursive call. For example, this one right here. And to check these questions, especially for the people who got answers for the questions, question 431 and 432 are examples of the substitution method. You can get an idea of how is it working. And the last resort when solving, when finding the runtime for a recurrence relation on the final is recursion tree. Recursion tree is you, instead of substituting the recursive call with the big O notation, which is like maybe the Cn squared that you might do, you replace the recursive call with the full equation again, taking into consideration the new input. That's definitely the most algebra intensive one. So if this method needed to be used on the final to find the runtime for one of the recurrence relations, it will probably be some simple algebra. It won't be very intense. So again, our logic for finding the recurrence, the runtime is, I'm going to see if it fits master's theorem first. If it doesn't, I'm going to take a look at the question. Does it tell me prove if it's big O of something? That means I'm going to give substitution method a try. If that's not the case, my only option is the recursion tree. Okay, so that's almost everything about finding runtime. Now, the way we want to study for this is pen and paper and just solve a couple examples of these problems. So as I said, check pages 95 and 96 for the master's theorem, and check pages or check the questions 431 and 2 for the substitution method questions. And the chapter right after 4.3 will be the recursion tree. The thing is with the book, they don't do much good detail into explaining how is it done. So probably the lecture notes are the best option. Okay, so that's finding runtime. Usually there's like 20 points about it. So it's something that you don't want to waste. 20 points could easily be gotten through here. Maybe you'll make an algebra mistake here and there, so that's not a big deal, but you want to probably get the majority of these points. And also another comment is with the master's theorem, he has the theorem written on the exam, so you don't have to memorize it. Okay, so that's finding the runtime. The next topic is I want to talk about is sorting. With sorting, probably the first thing we need to do is know the specific algorithm for, or know the specific steps for the algorithm, and know the intuition behind it, and knowing the runtimes. So to know the runtimes, on page 150 from the book, there is a table for all the runtimes. And I can give you what it looks like right here. So that's in the book, and now you have access to the slides too, so you can always reference it. So that's a really helpful table to use for runtimes of sorting algorithms. Okay, So we know the runtimes, and the reason we want to know the runtime is not necessarily to run the algorithm, but at some point in the midterm, we might be faced with a performance type of question. It's like, oh, if I used a computer and I have a computer that is twice as fast and I'm running those two sorting algorithms, what should be the time, the time to finish the algorithm? For these type of questions, you need to know the runtime for the algorithm. Okay, so that's the first point. So another thing to take your understanding of the sorting algorithms to the next level, and probably to the level of the final questions, the questions on the final, will be to know what input that will cause the worst runtime for an algorithm. And to kind of get a sense of it is if we looked at this table and we looked at the average case. So the average case is if we ran the algorithm on a random set, we expect the runtime to be this average case. But if I gave the algorithm a specific input, I will be able to produce the worst case. Just a comment, you guys can see my cursor, right? Okay. So know the input that will take the runtime from the average case to the worst case. The input might be hard to find for some algorithms, but in the class we went over a couple algorithms we found out what would be the input. It could be the reversed, it could be the input when it's split in half and there's like some weird permutation of the input. And really when we're thinking about the input to produce the worst case, usually when it comes to comparison algorithms, we want to think about the input that gives the most number of comparisons. If my input causes a lot of comparisons, that means it's the input that's gonna get me the worst case. So that's something that is important to know about sorting algorithms. So, and the questions regarding sorting algorithms, again, it will be a question that goes just run the sorting algorithm on this maybe data set, or the final question for a sorting algorithm could be something like make a tweak on the sorting algorithm where maybe if you want to change a step in it and run it on this input and show me the result. Also, it might not only be show me the result. If a sorting algorithm is comparison based, the question will be like, oh, show the order of comparisons. So it's important that we know in what order are the comparisons are happening. So one of the biggest questions for the sorting algorithms is usually a quicksort algorithm. So the format for the quicksort algorithm is run quicksort. The professor will tell you how to pick the pivot, and the partition method is usually you slide the pivot and you slide everything smaller to it and larger than the pivot to the left and the right without messing with the order. So you can think of the partition as a way to partition the big list in place and what did I call it? And not mess up the orders of the order of the items. Then he will look for the comparisons done in each round, and yeah, the comparisons done in each round in order. So the order of comparisons matter. He will be looking at these details. So that's quicksort. There was also another small idea related to quicksort, which is quick select. Quick select was mentioned in one of the videos, and we know that the goal for quick sort is to sort a list, but for quick select, the goal is to find a specific item versus sorting an entire list. So usually the answer or the question that quick select tries to answer is that I want to know the fourth largest element in a list. So what quick select do is, instead of sorting all the list and going to that fourth element and taking it out, I'm gonna not sort all the list, only sort the necessary parts of the list to get maybe the fourth largest element. And the way it could happen in the context of quicksort is that if I'm looking for the fourth largest and my pivot is a little after the fourth position, after I put it in the middle of the list, that means I'm only going to work with the stuff on the left, because I just realized that the right and left for you guys will be reversed. Okay, let me pull out maybe notes. Actually, we'll do here. So let's say I'm going to be explaining quick select quickly. So let's say I have the list 3, 4, 7, 3, 9, 1, and 8. Okay, so at this point, I will ask, what's going to be the pivot here? If you guys read the questions from before. So the pivot for this list will be 8. And what I want to do with the 8 is oh, the 8 is probably like a bad choice for the pivot, to be honest. So let me do 4. And 4 is going to be the pivot. So I'm going to slide 4 to its correct place. But you want to keep in mind, what are we trying to ask? What question are we trying to answer here? So let me find the the third smallest element. So this is my list. What I'm going to do with it is I'm going to slide my pivot to the correct place. So 3 will stay the same. 3 is less than 4. And I have another 3 less than 4. And I have 1 less than 4. Then my pivot. Then I have the 5. Then I have the 7. Then I have the 9. Then I have the 8. Okay, so we can notice that with this partition, we just slide the elements that are smaller than 4 to the left of 4, and anything bigger than 4, we slide it to the right. And notice that the order of the 5, 7, 9, 8 stays the same. So 5, 7, 9, and 8, and they keep the same order after we partition. So this is how we're going to do the partition for the final. But here, since we're working with quick select, I did my first partition. I'm looking for the third smallest. My third smallest will be sitting in this partition because it's of size 3. So I know for sure that the smallest third element will be on that section. So I'm not going to touch the right partition. That's the idea of quick sort. I'm going to take the left partition. I'm going to run quick select on it again, which is picking a pivot, moving it, and choose the right or the left to work with based on my question. So in a way, you can see that with quick select, we can find maybe the fourth element, the fourth largest or the fourth smallest, depending on the question, without doing a lot of the work that quicksort is doing. So that's usually a very important question in the midterm or the final, and it might get a little tricky, but it's an important one. It will definitely show up. Okay, so that's sorting. Again, the table was on page 150. It's really important. Let's talk a little bit about data structures. Data structures. So what we took so far is stacks, queues, and linked lists, and those probably don't need a lot of explanation. They're intuitive data structures. The more complicated ones are the heaps. So with the heap, there is something called a heap property, which is depending on what type of heap you have, the property could differ a little bit, but it's and then essentially it's the same concept. The two types of heaps we have so far is the minimum heap and a max heap, and the way the heap property changes reflects that if we have a minimum or a max. And the heap property for maybe a max heap is the parent is larger than the children. It's not that the parent is larger than the left and smaller than the right. It's that the parent is larger than the children. Okay, then that's the heap property, and we have to make sure that this is the case for a minimum heap or a maximum heap. Then the heaps are usually binary heaps. That means each parent will have two children. So with the heaps, it's important to know how they work, how insertion works, how build heap operation works, especially if we have a list. A question could be, here's a list. I don't know if it's a heap or not. The question could be like, okay, this is a heap that is not correct, but conduct some heap operations on it, like inserting some elements and delete max or delete min, which is the root of the tree, of the heap tree. So these heap operations are important. It's also an important skill to know if you're given a list and you look at the list in the midterm or the final and you go, okay, this is a proper heap, this is not a proper heap. Usually a good resource to kind of visualize what a heap list looks like or what you expect it to look like is this Wikipedia picture. If we Googled heaps, this one. So if you were given a list, you want to visualize the list this way, where the root is 100 and the next two elements are the children of the root. Then after those two elements, the ones after are the children of the fur of the 19 and going on. So this way you can take a look at a list and maybe draw the tree quickly. This is a helpful picture that I've always used when I had this class. Okay, so that's heaps. Then we also touched on binary search trees. And the binary search trees, they have also something called the binary tree property, which is the property that says the left child is smaller than the root and the right child is bigger than the root. Also, insertion operations on binary search trees are important to know how they are performed. Is, oh, you go from the root, then you compare, then you know if you want to go left or right, and you keep doing that. Okay, so that's binary search trees. I didn't see a question about binary search trees so far, but they're simple data structure in general, so it's not that big of a deal. Insertion when operations on them are not that complicated. Then the last data structure that we touched on was B trees, and you can think of it as balanced trees, because the problem with the binary and heaps that they tend to skew to maybe a certain direction and maybe start looking like a linked list. The balanced trees is aimed to solve this problem with the heaps and the binary trees. And the types of the balanced trees we took so far was the 2-3 tree, and we did a programming assignment about it. And some of the important stuff to know about these trees, number one is that it is an important question on the midterm. If it's not on the midterm, it'll probably show up on a final, some type of balanced trees. And what's important to know about them is a couple of the operations, which is insertion. How can we insert through a balanced tree? especially knowing how many nodes, how many keys a node could have, and based on the number of these keys, how many children I will have. And again, the example was 2, 3 trees. And the insertion is similar to what we do with the heaps and the binary search trees, except that we have to keep our attention for an idea of splitting. Like whenever we insert or whenever we overflow a node, that means we have to split it, and we have to know how the splitting happens, and we have to also to remember that if the splitting was happening inside the tree, that means the tree level will not increase. But if the splitting is happening at the root, that means the tree level will increase one level. So those are some of the important operations to know about balanced trees. There is a really good chance that this question will show up. So that's the balanced trees. Again, the second point was like keeping track of the number of children for each node. If we have a tree that can take maybe 4 keys, that means it could have 5 children. And we have to consider those keys and the ranges specified between each key and the other, so a child could go in between. Okay, so that's it for the data structures that we have. Surprisingly, it's not like a lot of data structures. We worked mainly with trees, and that's usually the important data structures that we need to worry about. Okay. Now we'll talk a little bit about graphs, and that this section of the semester took quite a bit of time, but I'll piece it all together in those 3 slides. So with the graphs, we started with talking about graph traversal, and usually with the graph traversals, it's probably the first thing you want to learn about a graph, because a traversal algorithm tells you how can you go through a graph, how you can loop through graph nodes. And if you want to do anything on a graph, you want to know how to traverse the graph. And the common traversing algorithms are breadth first search, which is BFS, and depth first search, which is DFS. And the nice thing about these algorithms is that the name gives an intuition of how the algorithm will work. For example, depth first search tells you that I'm going to get to the deepest node possible in this graph, starting from the source. Then I'm going to go up and explore the rest. So I'm going to explore the depth first. I'm going to go to the deepest possible node. Then I'm going to explore the rest of the graph. But with breadth first search, it is going through the graph one level or one layer at a time. So imagine if you're starting from a specific node, you explore all the nodes that are 1 edge away, then you explore all the nodes that are 2 edges away from the node you start with. And it's also important to recognize that BFS uses a queue to do that like layered type of exploration of the graph, and DFS uses recursion to get to the deepest point in a graph. So DFS, BFS, there won't be explicit questions about these algorithms in general. Like it's not gonna be, there won't be a questions like, oh, here's a graph, use BFS and like tell me something about it. Maybe about DFS is, if we reference the book, there's this notion that, oh, this is a back edge, or this is a forward edge, or this is a cross edge. Maybe a question about that could be possible, is to know how to label the edges through DFS. The book chapter about DFS has a good example where they label the edges forward, cross, or back edge. They have definitions for these edges, and the way they do it is through coloring them. It's very good visualization to use. So that's the graph traversals. Then after we finished knowing how to traverse a graph, we start looking at topological sort. And with topological sort, we realized later on that it's important to know how to topologically sort a graph, specifically for the programming assignment for the job scheduling. All right, so with the topological sort, we have two algorithms. We have the DFS-based one, which is you run DFS first, then what do you do after running DFS? Oh, you run DFS first, then you take the nodes and decreasing finish time. So what you just saw is me trying to remember the intuition behind finding a topological sort. So the DFS base is I'm going to run DFS, I'm going to record the finish times, then I'm going to take them in decreasing order, and I will get my topological sort. Then also there was Kahn's algorithm. Kahn's algorithm was not in the book. I looked for it for like a good 5 minutes. I wasn't able to find it. It's in the videos. Okay, and also there was another comment on DFS. So other than the fact that you have to know the labels for the edges forward, back, or cross, is also knowing how you can compute the finish times and the start times for each node. It looks like for DFS specifically, it looks like it could be like a substantial question. It's like, here's a graph, run DFS, give me start nodes, start time and finish time, and give me the labels for the edges. That could be a question worth 10 points. So, and there's good details to a DFS, so this should be known for sure. Okay, so going back to topological sort. So there's the DFS base, there's the Kahn's based, and the Kahn's was the one through the video. I wasn't able to find it in the book. And what we need to notice for the difference between those two is that with DFS, if my graph had a cycle, the topological sort produced by DFS will include the nodes in that cycle. However, with Kahn's algorithm, the topological sort produced by it will not include the nodes the nodes that are part of a cycle. So I'm going to comment it. Result does not. I don't know how to write does. Include cycle nodes. But with DFS, result will include cycle nodes. Okay, and that was an important distinction that we realized when we were doing the job scheduling assignment, is that, oh, if we used Kahn's algorithm, I really don't have to worry about the cycles. They won't be in the job schedule. Yeah, and that's the difference between both. Also, another comment about Kahn's algorithm, it uses a queue inside also to do topological sort. Okay, so that was the topological sort. Also, we can talk a little bit about what does it mean to topologically sort a graph. Probably the best way to visualize it is if I took that topological sort and if I draw all the edges, there will be no edge that is pointing backwards. All the edges will be pointing forwards. So in a way, since that's the case, it is some type of a sort for a graph. You put it in a specific order where all the edges are pointing forward. And we will see that the topological sort will give us some advantages into processing graphs. If I processed a graph using its using the topologically sorted nodes for that graph, I will get some advantages. And yeah. Okay, so that was topological sort. That's what we have about topological sort. Now, strongly connected components. So with that, running the algorithm about strongly connected components on a graph, it will tell you if a graph has different strongly connected components within it. And to define strongly connected components, they are the components, or they're like a collection of nodes that they're reachable from each other. So if I was at 1, I can reach all 5 from this specific one. Maybe I have a bigger graph, but this is a strongly connected component within this graph. That means I can reach all the nodes within this strongly connected component from any node of this component. And the algorithm to run it, to find the strongly connected components, is also something based on DFS. So the intuition behind it was, I'm going to run DFS, then I'm going to calculate the finish times and everything. Then I'm going to get the topological order from that by getting the decreasing order of the finish times. Then I'm going to reverse the graph, get the complement of it. Then I'm going to process the nodes of that reversed graph using the topological sort that I got initially. And eventually, you will be able to find the strongly connected components. Strongly connected components is an important topic too. I remember personally doing it for one of the questions in the midterms. So that's, we're still not done with the graphs. So the other aspect with the graphs was the minimum spanning tree. And the idea of a minimum spanning tree is, let me find the cheapest way possible to traverse this graph. When I say cheapest way possible, you probably can think is like, oh, I'm looking for the cheapest way. That means it's probably a graph with weights, or where the edges have weights. And there's 2 algorithms for it. There's the Kruskal and there's the Prim. And usually the result of these algorithms is some type of a tree that is the minimum spanning tree for a graph. So this could be a question where, oh, here's a graph, give me the minimum spanning tree. Give me the minimum spanning tree where it's going to give me the ability to traverse this graph the cheapest way possible. So that's minimum spanning tree. All right, SSP, single source shortest path. So this one is, there's like 3 algorithms to do this, and it's not fun, to be honest. So we'll start with the first. So Bellman-Ford, or let's talk about single source shortest path in the beginning, to begin with. So with this, I'm trying to find, I have a source, and I want to try to find the shortest path to all reachable nodes in that graph. So usually the intuition for all these algorithms is, I'm going to mark that source node for 0 distance, and I'm going to mark the rest as infinity. Then I'm going to start running whatever algorithm that I have to find the shortest path to every possible node in that graph from the source. So there's Bellman-Ford. With Bellman-Ford, we can have negative weights for the edges, but if we have negative weights for the edges, we can't have cycles. Because imagine if we have if cycles were possible and negative weights were possible, that means we're running the risk of having a negative weight cycle. So that's Bellman-Ford. Single source shortest path for in a DAG is exploiting the fact that this graph is a directed acyclic graph. So I'm going to run a specific algorithm that is efficient. That's going to probably depend on finding the topological sort for that graph, because it's directed acyclic graph, and find all the find the cheapest or the shortest path to all possible nodes. And with this one, also negative weights are possible. It's not a problem. It's just we can't have cycles. And it makes sense to not have cycles, right? Because it's a directed acyclic graph. So that's that. Then we have into the last one is Dijkstra's, and with this one we can't have negative edge weights. I don't know why I had it in green. This should be in red. No negative edge weights and no cycles. And the reason we don't want to have negative edge weights is because we use a queue, and since we mark the source as a 0, and I have a negative edge weight that maybe caused some node to have a negative distance, that means I will start with that first, and that doesn't make sense because we need to start with the source first. And here cycles are possible. It will take care of cycles without a problem. Okay, so that's single source shortest path. For these ones, expect any one of them to be a question. It's like, here's a graph, run single source shortest path algorithm. You will get the name of the algorithm, and you're probably going to have a matrix where you update all the shortest paths to nodes. Also, when it comes to single source shortest path, there's this notion of
sorry to interrupt. Can you hear me?
yes. What's going on?
Bellman-Ford can handle cycles, can't it? It just can't handle a negatively weighted cycle, like one that like sums to a negative.
A negative cycle. Well, it will tell you by the end of the algorithm. It will say that there is it will give you a Boolean, and it will tell you if there is a cycle or not. But for the algorithm to operate correctly and give you the correct result, there shouldn't be cycles. Yeah, because if we have negative edge weights and we have cycles, that means we have negative edge weight cycles, and that will make the algorithm fail.
Okay, because I thought it was that it could handle cycles as long as they didn't end up being like negative, because then you would be like have an infinite negative, like.
Okay, that shouldn't be the case, because that was the description of the algorithm in the introduction for Bellman-Ford.
Okay.
Yeah.
What did you say?
Okay, so that's that. Let's make sure that we don't jump in on the voice, because that's going to be on YouTube at some point. Okay. Let me actually check Bellman-Ford. So with Bellman-Ford, it's the edge weights might be negative, so negative edge weights are possible. And if you checked the last, there's the last line. It says the algorithm returns true if and only if the graph contains no negative weight cycles that are reachable from the source. So it's saying that the algorithm, in order for the algorithm to run correctly, we can't have any negative edge weight cycles. And for us to not have these cycles is we can allow negative edge weights, but we cannot allow cycles because the combination of both might give me negative edge weight cycles. So you can check page 651 on the book. And so that's the book explanation for it. So also maybe you can think about it as to prevent negative edge weight cycles, I can have cycles but no negative edge weights, or I can have negative edge weights but no cycles. So maybe I could update this to be the following, because it makes sense. It makes sense for the comments that I got in the chat that yeah, it will work if there's cycles but no negative edge weights, either or. So I can have negative edge weights but no cycles, or I can have cycles with no negative edge weights, and it will work. It's just we don't want to run into a situation where I have a negative edge weight cycle. Okay, and that is single source shortest path. Or is that, was I clear on the Bellman-Ford so far? It makes sense? We can have either or. So it's either no negative edge weights and we can have cycles, or we can have cycles but no negative edge weights. The book has it in a certain way. Probably the videos have it a different way. Okay, so that's single source shortest path. Let's move on to all pair shortest path. So with all pair shortest path, we have Floyd-Warshall, and that's the only algorithm that we know. With Floyd-Warshall is we don't want to have negative edge weight cycles. So in a way, we're running through the same thing that we just ran into, is we don't want negative edge weight cycles, but maybe we can have the negative edge weights and only, or we can have the cycles only. So with this algorithm, this is a really important one, and it's one that is a little tricky to get correctly. But if you look at it, and it's like, if you see the question, it looks a little intimidating, but it's not too hard to get the 10 points out of this question. This is for a really important question. So what's important about this algorithm is to know what the pi table is. So the pi table says, I'm just gonna record the last node in a path. So whenever I make a new path, maybe including node 4, which is the last node in this new path that I made, I go to that entry in the pi table and I update that, oh, my last node is 4. And to get how this works fully, in page 696 in the book, they have like a run through of how the pi table will be filled. And there's the phi table, and the phi table holds entries to the biggest node on a path. So let's say my path has nodes from 1 to 6, or like, let's say my path has include nodes from 1 to 6, yeah. And if I update this path with a new path that has a node 7, that means I have to go to the phi table and say that, look, my largest node on this path is a 7. That's what we need the phi table for. And again, this is an important question. It will probably be, it's either on the second midterm or the final. Floyd-Warshall is really important. And yeah, I think it was on one of the practice midterms, I believe. And the answers for that should be there. So that concludes our graphs section. The graphs section was pretty dense because we start with the traversals and we go through topological sort and strongly connected components, minimum spanning trees, SSSP, and all pair shortest path. So just because it's big, it's probably expect 2 or 3 questions from graphs. Like, yeah, probably 2 or 3 questions from this section because it's a big section. Now, dynamic programming. So for dynamic programming, there's only the general idea that we have to know behind dynamic programming, which is, instead of me doing the same work again and again, and the example was Fibonacci, I'm gonna take that work that I did and I'm gonna save it in an array, and I'm gonna have access to this array through each recursive call of that algorithm, and I'm gonna check if I have the answer, and if I have the answer, I'm gonna just take it from the array, and if the answer is not in the array, I'm just gonna calculate it. So that's the general idea of dynamic programming. Usually there's only one question about dynamic programming, and with my personal experience, I skipped the question with the dynamic programming, because it's like you have to concentrate too much on it. And it's like if the idea already feels a little hard, you will waste a lot of time on the final trying to nail one question, where you can probably get other questions a little faster. Because with this final, it's not only about knowing the material, it's also about the technique you follow answering the questions. But that's the general idea of dynamic programming. I'm saving the answer instead of calculating it every time. With the MP completeness, so a problem with MP complete is a problem that is hard to solve. It's like really hard to solve. But if you gave me an answer to that problem, or let's call it a valid answer or a correct answer, that means I can take this answer and I can run an algorithm to verify that your answer is correct. And this algorithm will take polynomial time. So given a correct solution, I can verify the solution in polynomial time. That's the idea of an NP problem. And there's this notion of being NP complete, which is being NP and NP hard at the same time. So the next slide is I also want to touch over how can we maybe transition from one to another and prove. What I wanted to say something else here. Okay, I'll probably remember it. Okay, so also with NP completeness, a possible question could be, let's say we have a problem X, and the question says that this problem is NP, and the question tells you to prove that it's NP hard. So what you want to do is you need to find another problem Y that you can reduce. This arrow means I'm trying to reduce, that you can reduce to this problem X that is given in the question. So now you can ask what this problem Y could be. And this problem is one of those problems that we took in the class. So it could be the click problem, it could be the vertex cover problem, it could be the independence set problem. So those problems, we know that they are NP hard, and they're NP too. So if we can find a way to reduce the problem to the problem given to us, we just prove that X is NP hard. And for a midterm or a final question, the reduction process or the way to reduce a problem to another should not be that hard. It should be a little intuitive, as long as you know what is the click problem and what is maybe the other NP problems that we took. The reduction should not be that hard. This problem X is probably like a small variation of the other problems, and we can reduce it easily. Or he can always do one of the reductions that we did in class, because what we did in class is we reduced the vertex cover to a click problem, and I think we reduced two more problems. So with that in mind, or with that in the notes, that could be one of the reductions that you have to do on the midterm. So it would be actually worth it to actually memorize these reductions, and because he could be like, oh, here's a problem that is like very similar to the vertex cover, and prove that it's NP hard. So the only thing you need to do is remember the reduction of a vertex cover to a click, and just you can answer the question. So that's one variation of the question, is to be given a problem and being told that this problem is NP and you want to prove it's NP hard. Or it could be like, here's a problem X, we don't know that this problem is NP or not, we want you to prove that this problem is NP. So what you need to do is you need to find a way to reduce that new problem given in the question to a problem that we took that is NP hard. So yeah, that would be the questions about it. And personally speaking, with these type of questions, I skipped these types of questions too, because I was like, I don't want to think about the reduction in general. So what anything that related to NP completeness, I'm gonna maybe not skip completely because I used to understand it a little bit, but I'm just gonna leave it till the end. All right, so that concludes the session. Maybe let me talk a little bit about strategy before closing. So it's important that maybe you set a strategy to do the midterm. Is if you feel like you're not confident with some topics, it should be fine of a person dropping the entire topic. I will talk about my experience. I did not solve anything that has to do with loop invariant. I did not solve anything that has to do with dynamic programming, and I did not solve anything that has to do with dynamic programming, loop invariant, and NP completeness. Those, like anytime I see a question, I was like, I'm just gonna leave it. I have more important stuff. I could be faster in other stuff. But what I made sure to do is know exactly how each algorithm works. Because if you're in the mentality that, oh, I'm gonna drop some topics, you better make sure that you can answer the rest of the questions. And that's a strategy. So make sure you put a strategy for the midterm. It will be curved. So yeah, that concludes the session for the semester. This session is just like an overview of the topics, some comments on the important stuff, and that will be the last one. I don't know if this will be on YouTube soon, but I want to say it's probably will be on YouTube by maybe Tuesday or Wednesday. It will take a little bit of time, but the nice thing is you guys have access to these slides. It gives you like an overview of the entire semester. This table is pretty important, and it gives you reference to pages from the book to reference for the important stuff to look for. Okay, this wraps it up. Thank you for everybody who attended. Thanks for everybody who stuck with us throughout the semester. And I hope I did a decent job in like facilitating some of the material and maybe increasing the understanding a little bit for this material. It's something that I enjoy talking about and teaching in general. And so when I do it, like I'm doing it with passion, I guess. Okay, so good luck everybody on the midterms and the finals, and I guess I'll and if you guys ran into me on campus, don't be shy to say hi. All right, thank you and take care.